So we're on letter H now. Where is the particle when it changes directions? And we have our position function and we have our time. In other words, it changes directions when the velocity is zero, and we found out that the velocity is zero right over here. Here's our work. And by setting the velocity function with respect to time equal to zero, we found out where it was equal to zero at 1/3 seconds and at 5 seconds. So now we know the when, so we want to find the where, so we put those values in. And we've got this cubic, so there's a little bit of arithmetic to be done, but it's not that hard. Okay, so 1/3 cubed minus 8 times 1/3 squared plus 5 times 1/3 plus 10. That's going to be 1 over 3 cubed is 27, minus 8 over 3 squared is 9, plus 5 over 3, 3 plus 10. And we'll just try to get these to be one fraction. And common denominator looks like it's going to be 27, so we'll multiply by 3, and by 9, by 9. And we get 1 over 27 minus 24 over 27 plus 45 over 27 plus 10. And this is going to end up being 45 plus 1 is 46 over 27 minus 24 over 27 plus 10. And 46 minus 24 is 22. So it's going to be 22 over 27 and then plus 10. So 10 and 22 over 27, or 22/27 of a meter, because that's a position function. All right? Well, 13 and a half would be 1/2. So this looks like about, you could probably maybe say about 10.8 meters, almost 11 meters, something like that. 10.8, 10.7, somewhere between 8 and 7. That's a good approximation. So that's one place where it stops, okay? And the other one is S of at 5. We got 5 seconds was the other place where it stops. We put 5 in here, so that's going to be 5 cubed minus 8 times 5 squared plus 5 times 5 plus 10. 5 cubed is 125. 5 squared is 25. 8 times 25, 8 quarters is $2, so 200. Plus 25 plus 10. And that's going to be 25, and 25 is 150. Plus 10 is 160, so 160 minus 200. That's going to be negative 40, and that's going to be meters. And that's also where it's going to stop. Okay? So if we want to kind of describe the motion, we could draw a little line here, and we're going to start over here at, we can look at our position function, and when t is 0, our initial position is 10 meters. This might be 0, minus 10, minus 20, minus 30, minus 40. And that might be 20, so this might be 11. So we're going to start here at t equals 0. All right, and for 1/3 of a second, we're going to move to the right till we get to this point, which is about 10.8 meters. These are all meters. Okay, and then we're going to stop and go. So we're going to the right. We're going the positive direction from our directions over here. It's positive. So we're going right, left, right. So we'll start right. We'll go to about 10.8 meters. We'll stop, and then we'll turn around, and we'll go left for 5 seconds. So this is for 1/3 of a second. So this is when t equals 1/3. Then we'll go left till we get to negative 45, and this is going to be for 5 seconds. So t equals, well, this would be at t equals 5. So this is about 4 2/3 seconds to get from 1/3 to 5 seconds. And at 5 seconds we stop at negative 40 meters, and we turn around, and then we start moving to the right from then on out. So we go right a little bit, left a little bit more, then right a whole lot. We keep going right. And that's going to be for t greater than 5 seconds. So that kind of describes the motion. Now we can do this on our calculator. It's kind of easy to see that. So let's go back and review how we did that on the calculator. We put that in the parametric mode. So there's our parametric mode. And I got the little circle. We could put the regular circle there. And that's the position function. And we can go up here and we can change this to the little 0 and we can... I did the window. And I fixed my window so I'm going from 0 seconds to 10 seconds every tenth of a second. But I'm going, my x minimum is negative 50 because I'm going to have to go to negative 40. My x max is 40. Scale was 4 because I want to fit it all in there, and I just did y. Negative 3 to positive 3 and just 1. So when you graph it, you can see what's going on. Oops. Let's go back up here. Let's change this to the circle. And you can see it kind of moves. You can hardly see when it moves to the right because it moves to the right just a little bit for a third of a second. Then it moves to the left, goes to negative 40. And it keeps going to the right over like this. Okay, and I'll go back over here and I'll change it to the little circle with a tracer on there so we can trace it. So we just keep pressing enter and then we'll graph it again. And again, it just moves to the right ever so slightly, then it starts to move to the left. Which is what we came up with analytically without using the calculator. It's just nice. You can see now. Now let's go back and check it so we can go to the trace function. And see, you can check your time. Your time is at t equals 0, my position is at 10. Now, and we push the right corner over here. Now, see, I'm moving to the right. See, 10.4, my position is 10.421 at t equals 0.1. 0.2, it's bigger, more 6.68, 0.80, so I'm still moving to the right. Now, 3 1/3 is, I'm sorry, 1/3 of a second is 0.33, so between here now, I'm going to start going back to the left, so now it's getting smaller. Now I'm moving to the left, so you can see how the cursor's moving to the left. So let's go back. So if you look at the cursor, it starts moving to the right a little bit, and then it starts moving to the left. And you can mostly tell by your x values what's going on. It's going to go to the left, and we said to 5 seconds, so we can keep going until we get to 5, 4, 8, 4, 9, and 5, there you are at the negative 40. That's where we stop, and then we start moving to the right again. You see our values are moving to the right from negative 40 to negative 30, and just keep moving to the right, to the right, right. So that's what's happening. So you can check the trace function to check your analytical work. But like I said, you can figure it all out by all the information we got. So it's the same thing. Okay? Hopefully that makes sense to you. Now think about it. Try to thoroughly understand what's going on with this problem because it's an important one.